The amount of fuel required by Apollo 11 was 4.1 million liters, and the amount of fuel required by Voyager missions, both Voyagers, was just 300,000 liters. Apollo 11 just went to moon and came back to Earth. And Voyager 1 and 2, they are still traveling after 22 billion kilometers away from Earth. If you apply some general sense, the amount of fuel required by Voyager missions would be many times the fuel required by Apollo 11, but it wasn't the case. Until 1960s, deep space exploration, space exploration beyond Moon, Mars and Venus, was thought to be not feasible because of two reasons. A, we didn't have big enough rocket to carry the amount of fuel required to go that distance. In fact, more the fuel required, the bigger the ship has to be, because fuel will require to carry more fuel. And second is, NASA just couldn't guarantee for how long the satellite would be in working state post few months. Forget about 30 or 40 years, the time it would require to reach Neptune. But still, Voyager 1 and Voyager 2 made it, and even past that, and still working. So how did we manage to do that? How did we manage to achieve such feat? Now, you would not believe that mathematics behind it is pretty simple, and it required an out-of-box thinking to achieve Voyager 1 and Voyager 2. When Sputnik 1 was launched in 1957, there was a race to reach the next destination, which was Moon, Mars and Venus, which happened in very short time. But beyond that, deep space exploration was thought not to be feasible, because when a rocket launches from Earth, it has to go against the gravity pull of Earth. But once it is out of Earth, then it has to also go against the gravity pull of Sun. Just to give you a number, the speed that rocket has to achieve to escape the Earth's gravity is about 11.2 kilometers per second. And to escape Sun's gravity at the distance of where we are, the Earth, it has to achieve 42.3 kilometers per second. As you know, Earth is already in motion, so in a way we already get 29.3 kilometers per second. So what the spaceship or the space rocket requires is just another 12 kilometers per second, and it requires enormous amount of fuel to go against Sun's gravity. So in 1961, a 25-year-old graduate called Michael Minovich arrived into scene, and he was working on something called as a three-body problem. A three-body problem involves in predicting the motion of three objects interacting gravitationally, like a spacecraft interacting with both planet and sun. Mathematically, it's incredibly complex because there's no straightforward solution. Each body motion affects other, creating constant changing forces and trajectory. And Minovich was not the first guy. In fact, this problem has persisted for more than 300 years, right from the greats like Newton to this day. So in 1961, Minovich, then a graduate student, had access to one of the fastest computers at the time, the IBM 7090 or 7090. He decided to use this computer to simulate different scenarios in three-body problem. Minovich was curious about how spacecraft's trajectory might be influenced by gravitational pull of both sun and a planet. During these simulations, Minovich noticed that a spacecraft could gain significant energy from a flyby of a planet. In traditional space travel thinking, a planet's gravity was often seen as a hurdle to overcome, but Minovich's work revealed that if a spacecraft approached a planet at a right angle and speed, the gravitational pull could actually slingshot it forward and redirecting its path. Now, this insight was revolutionary. It meant that spacecraft could reach distant planets without needing massive amounts of fuel. Instead, quote-unquote, borrow energy from a planet's gravity and carry that momentum to the next target. By carefully planning a sequence of planetary flybys, a spacecraft could even reach the outer planets, which seemed unreachable due to vast distances and the fuel limitations of the time. The Minovich findings laid the groundwork for using gravity assist as the core of interplanetary mission design. NASA later applied this technique for Voyager missions, using gravity assist from Jupiter and Saturn to reach Uranus and Neptune far more quickly than it would have been possible with conventional rocket propulsion alone. In short, by exploring three-body interactions, Minovich discovered that planet's gravity could be a tool rather than an obstacle for space travel. Now, this approach has since become the cornerstone of space exploration, allowing missions to reach farther into solar systems with minimal fuel requirement. As it turns out that in 1977, all the planets beyond Mars aligned. They were at one side of the solar system, giving a golden opportunity to use gravity assist or slingshot method to go past through all the planets and out of the solar system. This opportunity could not have been missed. Same type of alignment would have happened after another 176 years. So Voyager 1 and Voyager 2 was launched, and both Voyager 1 and Voyager 2 are the fastest man-made object ever built. In 2015, Voyager 1 passed Pluto and sent out beautiful pictures of there. Now both Voyagers are still active and sending scientific data after more than 40 years of their launch. And this is how an out-of-box thinking got us to deep space exploration. Thanks for watching, and I'll see you next time around. Bye bye.